I just wanted to introduce that to you guys really quick here. Yeah. So the final is going to work kind of similarly to the midterm that y'all did back in the 4th week of class. So it's not posted yet. It hasn't gone live yet. But it'll be posted the morning of Monday. So Monday morning, the final exam will be posted. And then you have all week to work on it. And then it'll be due on Thursday, the 17th. So Thursday is the very last day of class. And then for us teachers, we have to get our final grades into the office on Friday. So Thursday is going to be the last day that you can turn in any of your assignments, including any missing assignments that you maybe still have to go back and finish up, or the final exam. So I'm still working on the final a little bit, kind of putting the finishing touches on it. I should be finished up with that over the weekend. And then, like I said, it'll be posted on Monday, but not due until Thursday. So you'll have all week during that last week of class to work on the final. So if you want to work on it for a little bit and then stop and then come back to it over the course of the days, that is totally fine by me. To help with that, like I mentioned, our Tuesday, Thursday class next week is going to be all about reviewing stuff from the last several weeks. So going all the way back to talking about the properties of matter, like the solids and liquids and gases and the chemical changes, the atoms, the neutrons and electrons, their shells, compounds and the different types of bonds, chemical reactions. There will not be any balancing chemical equations questions on the final. So if you still don't fully understand that, don't worry about it too much. It's not going to be covered as part of the final. And then finally, the stuff that we talked about earlier this week about the SI units, the metric units, and some density questions. So all of those will be on the final. Again, the final will go up next Monday and be available throughout the entirety of the week, with the last day to turn in not just the final, but any sort of material being on Thursday, the 17th. So normally I let you guys have a little bit of wiggle room when you're turning in stuff late. I like to say I don't really care when you turn it in, as long as you get it to me at some point. But the very last day for you to turn anything in will be the 17th. Any work that gets turned in after that, I'm not going to even look at, and it's going to go down as a missing grade or a 0 in the grade book. So make sure you get your final finished by the 17th. You have any final assignments or missing assignments turned in by the 17th. And then the nice thing is that next week, your daily assignment questions are going to be really kind of simple, easy to answer questions about things that worked for you over the course of the term, things that maybe didn't work. So like the topics that you like the most, the topics that you like the least, any suggestions you have for me to help make this course be even better for future terms. Those are the kind of questions that'll be going up for your daily assignments on next week. So there's not going to be any like big major homeworks to finish last minute or anything like that, since I know y'all will be working on the final. And so it'll just be a simple series of questions just so that you can do that daily assignment and get that attendance for the day. All right. Anybody have any questions so far on the kind of basics of the final or the last week of class that we got coming up?
No, sir.
All right, good to know. So with that being said, Let's go ahead and jump into the notes for today. So Tuesday, we were talking about some different sort of basic types of measurements, things like mass and length and volume with our grams, our meters, and our liters. Today, we're going to be talking about a slightly different type of measurement. One of the things that is a physical property that an object can have, that a substance can have, and that is the density of a substance, of some sort of matter. So density, you might have kind of like a general idea of density, like if things are really dense versus if things are very not dense. But today we're going to talk about what exactly density means in sort of the scientific aspect and how we can figure out density if we know a couple different measurements of our substance. So when you think density, you might just think like, oh, heavier things are more dense. And while a lot of the time, part of that is true, density is not just the measurement of how heavy something is, it is the measurement of the compactness of a material. So how tightly compacted are the atoms and electrons that make up our material? So how close those atoms and molecules are to each other, and how many of them there are in a certain amount of space. So density is not just related to the weight of an object, it's also related to its volume, or how much space that an object takes up. So yesterday, we were talking about weight in terms of mass, in terms of like the grams versus the kilograms and stuff like that, and volume being the liters or milliliters or centimeters cubed. So density is how the weight and the volume kind of interact with each other. So everything has density. So obviously solid things, a lot of material in there, so they're pretty dense. Liquids are also dense, and even gases, which you might not think about as having density because it's like, oh, they're invisible, they're lighter than air, they're floating all around us. Even though they're so light and spread out, they still have density as a gas. It might be a really, really low density, but they still have a measurable density. So density is all about compactness. It's about how much atoms or molecules that we can fit into a certain amount of space. So the more compact the material is and the smaller the space it takes up, the more dense that it is. So some substances are less compact. Their atoms and molecules are kind of light and spread out. Other substances are more compact, where their atoms and molecules are really, really closely tight in together. So the less compact material is less dense, and the more compact material is more dense. One kind of good example that I like to think about, and this might just be on my mind because it was my garbage day earlier today, is thinking about like the garbage can in your kitchen, right? The actual bin, the actual can itself is one kind of set space, right? It's so tall and so wide. But when you first fill up that can with trash, do you look in, see that it's full, and be like, oh, totally full, we got to take it out to the dumpster? For the most part, no. Most people will take paper towel or take their hand and reach in there and push that stuff down because it's all, a lot of times it's like papers and plastics and things that you can squish way down so you can add more trash in on top. By doing that, you have increased the density of your trash can. You've gone from less compact plastic wrap and paper and maybe some like trash, some junk mail that you threw in there. That was in there at first. And then you smushed that all together and added even more trash on top, so you made it more compact. You had the same amount of space, but you put more stuff into there when you squished it down, so you increased the density of your trash. You made your trash more dense. Same thing happens when they take that trash and put it into the big garbage truck, right? I don't know if you guys have ever watched the garbage truck come by and pick up the trash, and they shove it into the truck and then they drop off your can. And then it has that big kind of scooper arm that comes down and squishes everything to the front of the truck, because they want to try and fit as much trash as possible into their truck so that it doesn't get too full and they have to do multiple trips. So they try to compact and get the trash as dense as possible. So that's what we're talking about. Filling in a certain amount of space with more and more material will make it more compact, more dense. So more spread out, taking up a big area, your density is going to be lower. More compact, taking up a smaller area, your density is going to be higher. So kind of more scientifically speaking, density is the amount of matter per unit volume, meaning it's the amount of stuff for the volume of your container. So if we're going along with our trash example, it's the amount of trash per trash can. So it's this ratio of mass to volume, how much stuff you have compared to how much space that it takes up. So with our trash example, if the volume stays the same, you have the same trash can, but you increase the mass, you put more trash in there, you make it heavier in there, the density goes up. You had the same space, but more stuff got compacted in there, so your density went up. On the flip side, if the mass stays the same, but the volume increases, so say that you took the little baby trash can from your bathroom and dumped it into your empty kitchen trash can. Now you have a decreased density because you have the same amount of trash, right? The little baggie of trash, but now it's in a much bigger area. So if the mass increases, if you get heavier, you're going to get more dense. You get an increase in density. If the volume gets bigger, if you go somewhere where there's more space, the density goes down. The density decreases. So again, density is this ratio. It's this comparison of mass, the amount of kind of the heaviness of an object, to volume, its space that it takes up. So based on these two measurements and these two observations, scientists were able to come up for a relatively simple formula to help explain density. So density is equal to mass divided by volume. So if nothing else, this should be your big takeaway from the notes today. This is sort of like if I could put big stars on this slide, then I would. So density is mass divided by volume, a lot of times said as mass over volume. The mass is usually represented in grams, and the volume is usually expressed either in centimeters cubed or liters or milliliters. So weight over space, mass over volume. So if you know the mass of an object and you know how much space that it takes up, you can do mass divided by volume, and that will result in your density. So density equals mass divided by volume. So because this is basically a very simple math equation, that means that we can do some kind of basic moving around of our different variables, of our different measurements. and use this kind of expression to also figure out our volume if we have the mass and the density, and what is our mass if we have the density and the volume. So like I was saying, if you're able to measure the mass and the volume of an object, then you can do mass divided by volume, and that will give you your density. What about if we change it a little bit? What about if you already know the density of some object, and you're able to measure the mass of that object, but you're having a hard time figuring out the volume? Well, luckily for you, you can do mass divided by volume, mass divided by density, and that will give you your volume. We basically just switched the volume and the density over here. So mass divided by density equals volume. If we know how heavy something is, and if we know how dense it is, then we can calculate our volume. And then finally, if we know our density and we know our volume, that means that we can calculate our mass. So in this case, we're doing density times volume gives us the mass. If we know how much space something takes up and we know what its density is, we can do this quick calculation in order to figure out the mass. So one way that's easy for some people to keep track of when you do divide and when you do times and stuff like that is something called this density triangle, or the DMV triangle, where we make a little triangle, separate it into kind of 3 parts, and put the M on the top and the D and the V down on the bottom. And I'll show you a couple examples in a second, but the basic way that this triangle works is that whatever you're trying to figure out, so say you're trying to figure out the density, to determine the equation for density, in case you can't remember it, you look at the other 2 letters. So I want to know density, so I'm going to look at M and V. M is above V, which means we do division. M divided by V is our density. If we want to know the volume, we look at the M and the D. The M is above the D, so we do divide again. M divided by D is our volume. And then finally, if we want to know our mass, our M, then we look at our D and our V. These guys are on the same level, which means you do times. And so D times V is our mass. All right, so I know sometimes it's hard for people to kind of keep track of all that just by using the letters to show everything. So I'll show you guys kind of a simple example with some basic numbers. So let's see, we got to do this, and then we got to do this, and then we got to do one of these and do one of this, and then do one of these here. All right, and then we got to share that with you guys. Here we go. So I'm going to start by making my little density triangle. And then it goes like that and like that. And we had M, D, and B. So let's let's say for our first example, I measured the mass of some sort of object is 21 grams and the volume is 7 centimeters cubed. So I want to figure out the density of this material. So I'm looking for the density. And I just can't remember the density equation off the top of my head. But I have this little chart over here. So let me look at the density triangle. I'm looking for D, and I have M and V. So M is over V, which means that we're going to do division. M over V. So 21 is our M, and 7 is our V. So whatever this object is, it has a density of 3 grams per centimeters cubed. That is our density of the object. I knew the mass and I knew the volume. And density is mass over volume. If I couldn't remember that, I can look at our density triangle over here. Mass over volume. M over V. So the mass is 21 over the volume, which is 7. So that gives me a density of 3. All right. So let's do another example. All right. So let's say I have a slightly different object. And I know that the density of this object is equal to 5 grams per centimeters cubed. And I know that the mass of this object is 20 grams. What I want to know is the volume. So, okay, I know D equals M over V. Okay, I got that. I know my density equation. But I want to know the volume, not the density. I already know the density. Okay, well, I can look at my little density triangle here and say, okay, I want to know the volume. I know the mass. And I know the density. So according to the DMV triangle, M is over D, so we do division. M is 20 grams. D is 5 grams per centimeters cubed. So 20 divided by 5 is 4 centimeters cubed. So my volume is mass divided by density. And if I couldn't remember that, I can look at my handy dandy little triangle over here. Mass divided by density. And the mass is 20, my density was 5, so my volume is 4. All right, let's do one more example of what happens if I want to calculate the mass of an object. All right, so I want to know the mass of an object. I happen to know that my density is 7. And 7 grams per centimeter cubed. And my volume is 6 centimeter cubed. So if I want to know the mass, and I know the density, and I know the volume, what am I going to do? Well, I can look at my triangle over here and say, okay, I want to know the mass. I know density, and I know volume. And according to my triangle over here, density and volume are on the same level down here. So that means that we're going to multiply. So the mass equals my density times my volume. So the mass of this object is 42 grams. So mass is density times volume. If I know the density and I know the volume, then I can multiply them together and they will tell me the mass. All right. So that's probably the biggest thing that we're going to talk about with density for this evening. So does anybody have any questions about the density equation, figuring out mass and volume and density? Any questions about what I was just going over there?
I just want to say hi, Mr. Stanley. Good to see you.
Hey, Cameron. Good to see you too. Thanks for being here.
Yes, of course. I'm here at work, but I'm watching.
All right. Awesome. All right. So does everybody kind of feel okay so far with our density equation and the way that we can use it to figure out not just density, but also mass and or volume?
Yes, sir.
All right, great. So let's jump back to our notes here. All right, so D equals M over V. Density equals mass divided by volume. If we know our mass and our volume, we can figure out our density. But on the flip side, that also means that if we know our mass and our density, we can do mass divided by density to find the volume. And if we know our density and our volume, we can do density times volume in order to get our mass. So a couple more kind of points I wanted to make about density and the things that can affect density in our different stages, going through gases, liquids, and solids. So like I mentioned, even though gases are very light, they're very spacious, they take up a lot of space, and they have extremely low weight, they do still have density. Different gases of different molecules can have different density. So one of the cool things with gases is that their density is often based on their temperature. So in gases, if you remember from way back in the second week of class when we were talking about gas, it has the particles that are the most spread apart from each other and are moving around the fastest compared to the liquids and the solids. And so in gases, the greater the kinetic energy, meaning the faster that these particles are moving around, that actually causes the volume of the gas to expand So as the gas gets hotter, its particles become more spread out from each other. And like we were talking about earlier, when we were talking about density, if we take up more space, if our volume gets bigger, that means that our density is smaller. So kinetic energy is related to heat. So we get that energy from increasing the temperature of the gas. So the hotter the gas gets, the more space the gas takes up, and the less dense that gas is compared to the cooler gas. So that's why cold air is more dense than warm air. As the air heats up, it has more energy and takes up more space. So it becomes lighter. It becomes less dense. The cold air, when it gets cooled down, it takes up less space. The particles get closer and more compact together. And so that air is more dense than the warmer air. So this is the science behind how hot air balloons work, actually. If you've ever seen one of those, they crank the little fire inside of the balloon, and that causes it to inflate and then starts drifting off the ground. The reason why the balloon rises, even though it's a lot heavier than the air around it, is that the gas inside the balloon is much less dense than the gas outside the balloon. The hot inside gas is less dense than the cold outside gas, the air outside. So the balloon rises because less dense things will rise above more dense things, which will fall below. There's also a reason why during the summertime, your upstairs feels hotter than your downstairs, even if your AC is going the same, is because the cooler air is falling down. It's more dense, so it's going closer to the ground, and the warmer air is rising. Liquids are also follow some of these principles. Cooler liquids tend to be heavier than warmer liquids. Different liquids will also have different densities compared to each other. So like in this glass here, we have what looks like some sort of oil, and then some water, and then something really, really dark, like, I don't know, maybe motor oil or something like that. And so these layers form with the liquids because our motor oil is the most dense, so it sinks down to the bottom. Our cooking oil is less dense, so it rises up to the top. And then our water is in the middle, and so it kind of exists between the lighter or the less dense and more dense liquids. Things that can also affect how dense liquids are is if you have a bunch of stuff dissolved in them. So like ocean water that has all of the saltiness in it from the salt water is more dense than fresh water. There's more stuff inside of the salt water. There's more of those salt crystals and stuff floating around. So there's more molecules inside of that same area. So that's what makes the ocean water more dense than the liquid water, because it has more stuff dissolved inside. So one really cool experiment that some scientists will sometimes do to show off density is mercury and lead are both fairly heavy metals. But the cool thing about mercury is that mercury is liquid at room temperature. So here's a scientist pouring some mercury from one glass to another. So mercury is one of the few metals that is liquid when it is at like room temperature, like 75, 80 degrees. So mercury has a density of 13,600 kilograms per meters cubed. Lead, on the other hand, another heavy metal, has a density of 11,340 kilograms per meters cubed. So which one of these is more dense? Is the mercury more dense, Or is the lead more dense?
Would it be the mercury?
Exactly. The mercury has a bigger number, so it is more dense than the lead. So because of that, if you take something that's made out of lead and put it into a pool of mercury, what'll end up happening is that it will float. So here we have this cup full of mercury on the bottom, and then this old school lead pool ball sitting on top, and the lead is floating on this liquid. This heavy lead ball is floating on this metallic liquid. And that's because the liquid mercury is more dense than the lead. So the lead is going to sit on the top and the liquid mercury will sit on the bottom. It doesn't matter that one is a solid and one is a liquid. All that matters is their respective densities. And since mercury is more dense, mercury goes on the bottom no matter what shape or size of the material on top. So solids are, in general, the more dense pieces of matter. They tend to have more density in them than gases or liquids, but their densities can be all over the place. So minerals, rocks, metals, wood, all of it can have very different densities to each other, depending on the type of material that it is made out of. One of the very few exceptions to this rule, and one of the extremely important for life on Earth exceptions, is the fact that ice is actually less dense than water. So think about when you get like a big Coke or something from McDonald's and they put a bunch of ice in there. The ice is going to float at the top, right? Even if you get a cup of water and put some ice cubes in it, the ice floats at the top of the water. That's because ice has an interesting property when it freezes. So when we go from water to ice, the way that the water molecules line up actually cause there to be more space in between them when they are frozen than when they are liquid. So this is why in the wintertime in places that are not Texas, but like Wisconsin, Minnesota, Michigan, places like that, the ice covers the top of the lake. It sits on the top of the water, but it does not sink down and crush all the fish and plants that are underneath it, right? Which would be very bad for anything trying to live in the lakes on Earth. So luckily, since ice is actually less dense than water, it floats on the top. That's also the reason why we have icebergs. It's due to that fact that if an ice comes off of an ice shelf, it doesn't just go into the water and sink down to the bottom. Instead, it floats around, sometimes accidentally bumping into a big ocean liner in the early 1900s and killing a whole bunch of people. That's not really important. The important thing is that the ice is floating even though it is a solid. So the ice is slightly less dense than the water, which is why solid water floats on liquid water. For most materials, this is kind of backwards. Most of the materials on Earth, when they freeze and become solids, they become more dense, and then they're less dense when they're liquids. Water is just one of those neat kind of exceptions to that. So we talked about how temperature can affect density, right? Both with gases and with liquids. The hotter that the material gets, the less dense it's going to be because the particles are going to get faster and move apart from one another further. Pressure can also affect density. Usually increasing the pressure allows you to fit more material into an area, which means that you're able to increase the density. This is the way that like oxygen tanks work for people that go scuba diving, is that there's a bunch of gas that's been compressed down and held at a relatively high pressure inside of that big metal tank that the scuba diver is using. And so the pressure in there is holding the gas in, and then slowly over time, as the scuba diver breathes, the gas gets released and the pressure goes down. But the reason why we're able to fit so much gas inside of that metal container is by increasing the pressure. And then lastly, one of the things that we talked about a little bit ago was that dissolved solids, especially in liquids, can affect and increase the density. So again, the more atoms and molecules, the more stuff that you have inside of a certain area, the more dense that your material is. So if you have not just water, but also salt and minerals and crystals floating around in there, that's more stuff in the water, which means that the water becomes more dense. So ocean water that has salt in it is more dense than fresh water that does not have salt. All right, so here's a kind of handy little table that shows the density for some common materials around Earth. So water is sort of like our baseline material for density. So the way that we calculate density, water just happens to be exactly 1.000 grams per centimeters cubed. So the density of 100% pure water is exactly 1. So whether or not things will float on the water or will rise up through water depends on their density. So, for example, air has a density of 0.0013, while water has a density of 1. So if you release air into water, is it going to float up to the top or sink down to the bottom of our water? So feel free to either share out loud or put it in the chat. If we mix air and water together, is the air gonna float up to the top or sink down to the bottom of the water?
You said lead and water?
The air.
Would it go up?
Exactly. Air is much less dense than water, right? 0.0013 is a much smaller number than 1. So air is going to float on water. Think about this is exactly what happens whenever you pop a Coke can and all those bubbles start fizzing up. Those are air, I think it's carbon dioxide for the most part, that is floating up to the top and escaping from the water. Before the can, the pressure from the can was keeping that air in, but when you release the pressure by opening the top, all those bubbles come up because they are less dense than the water that they're floating around in. What about wood, like a big piece of oak wood? If you took some wood and threw it into a pond or a lake, that would sink or float on the water in there.
Float.
Yep, float, precisely. So the wood has a little bit lower density than water. And so like if you've ever tried throwing like sticks or twigs or branches or logs into lakes or ponds, a lot of times they're just kind of float along at the top. Same thing for ice, like we were just talking about. Ice is a tiny bit less dense than water. As you can see here, ice has a density of 0.93. Water is 1.0. So ice is slightly less dense than water, but that difference is still enough to allow the ice to float on top of the water whenever you mix it in. What about something like aluminum? If you took like a big wad of aluminum foil and bunched it up and threw it into a pond, will the aluminum float or is it going to sink?
Float. I think.
Zinc.
So the density of the aluminum is 2.7. Water has a density of 1. 2.7 is higher than 1. So aluminum is more dense. So it is actually, like somebody just said, is going to sink. So the more dense that something is, that means that it will sink if you mix it with something that is less dense. The less dense thing will go to the top. The more dense thing will go down to the bottom. So then what about lead? Is lead going to float or sink if we throw some lead into water?
Sink.
Most definitely. Lead has a pretty high density of 11.3. Water is 1. So the lead is going to sink straight down to the bottom of the water. Same thing with gold. So gold is an even higher dense material compared to lead. It has a density of 19.3. So gold is very dense, which means that it'll definitely sink if you throw some gold into the water. I would not recommend doing that, but if that does happen, your gold is going straight to the bottom. So some other liquids that are slightly less dense than water include ethanol, which is essentially, it's the alcohol that is in our alcoholic beverages. Ethanol is a little bit less dense than water. So that's why if you ever have been to like a bar where they serve flaming shots, the way that they do that is they make the normal drink and then they put a little bit of extremely high alcohol liquid on top, either ethanol or Bacardi 151, something like that. The alcohol is a little bit lighter than the water and whatever the water is mixed with, so it'll float up to the top. And alcohol also happens to be a very flammable liquid as well. So the ethanol that's floating on the top of the water is what they light on fire in order to create that big effect of the flaming shot. And then methanol is another type of alcohol. It's one that sometimes gets used as fuel in different applications. It is even less dense than ethanol. And so methanol also will float on water. Again, the 0.79 of methanol, the density there is lower than the density of water, which has a density of 1. So depending on the densities of the material, the more dense material will sink down to the bottom of the container, and the less dense material will float up and sit on the top. It all has to do with that combination of mass and volume, weight, and how much space that it takes up. The more weight in a smaller space, the more dense your material. The less weight in a bigger space, the less dense your material. All right, and that, I believe, brings us to the end of our notes on density. So does anybody have any further questions? Anything about density that you're still not really sure about, or that you want me to go back and review a little bit further?
So the assignment that you posted today is based on this slide, correct?
So the assignment, I can actually do you guys really quick. So the assignment that I posted for today is all about calculating density, or sometimes calculating mass or volume, given the certain measurements that you have. So it says solve each problem below for density, mass, or volume. So pretty much all of these problems are going to be based on one of these equations that we went over in here. So we're solving either for density, for volume, or for mass. So it gives an example there at the beginning where a student has a sample of aluminum that has a mass of 27. So the mass is equal to 27. And the volume is 10. And it's asking about what is the density of this material. So like we were talking about, density is equal to mass divided by volume. And so we would do the mass, which is 27, divided by the volume, which is 10. And that results in a density of 2.7 grams per centimeter cubed. So the density of aluminum is 2.7. So that is going to work for the first several questions on here. So the question number 1 gives you the mass and the volume of some bread and wants you to calculate the density. Question number 2 gives you the mass and the volume of some wood and then wants you to calculate the density of the wood. Number 3 changes things around a little bit. It gives you the density, so it tells you the density is 4, and it gives you the volume is 25. And then it wants to know what is the mass. So I added in a little hint for you to help you remember your mass equation here. So mass is equal to density times volume. So if you do the density times the volume of the substance, you should be able to determine its mass. Similar kind of situation on number 4, although this one gives you a mass of 420 grams and a density of 10.5 and wants to know the volume. And then again, I provided a little hint that the volume equation is mass divided by density. And then number 5 and number 6 go together and they change things up a little bit more. It tells you the mass of a rectangular block. And then it doesn't tell you the volume directly. Instead, it gives you the dimensions of the block. So it says that we have a 2 centimeter by 3 centimeter by 25 centimeter block. So the first thing that you have to do for number 5 is calculate the volume of the block, where you do width times height times length in order to get the volume. And then in number 6, you use the volume from number 5 that you calculated and the mass from number 5 that it gives you in order to determine the final density of the block. So you figure out the volume, it gives you the mass, and then you use the mass and volume to determine the density. All right, so again, the equations are given to you on the homework, but in case you need a little bit help remembering, these 2 slides on the notes, number 5 and number 6, are going to be the most helpful when it comes to kind of checking yourself that you're doing the right thing as you're going through some of those homework questions. All right. There you guys. There you guys. All right. Does anybody have any final questions on mass, density, volume, or the density equations, or on the homework?
No, sir.
All right, hold on, let me. There we go. There's everybody. All righty.